Okay, welcome. This will start our lesson 4. This will be about what predictors do we include or not include in our model for it to be useful. So the first one we're going to talk about today is the overall F-test. Okay, so the big question is, what predictors do we include? Remember, in multiple regression analysis, for the general additive multiple regression model, there are other models as well, but for this model where each of the terms are added up, we're assuming the error random variable has a mean of 0 and a constant variation of sigma squared, and that the residuals are normally distributed. So we want enough predictors to be useful, but not too much that we overfit the data. And so we're taking in some things that are irrelevant and kind of messing up our model. So first of all, the question is, why not the coefficient determination of R-squared? If we have an R-squared, then that's a pretty good model. But the problem is, you can inflate R-squared by just adding more and more predictors, even if most are unfrivolous or unnecessary. So we need a better test than just looking at R-squared. So the question we're going to start off with, does any of the predictors add value? Any at all? So for example, we're looking for righteous people. They have all fallen away. They're all like depraved. There is none that does good. No, not one. So none of our predictors are any good. Now, just as an aside, our worth from God does not come from our utility, but our inherent worth. But we're just talking about utility and misusing the Bible verses for today. So again, this video will be like, do any of the predictors explain the variability? The second question will be, does a particular partial slope contribute, or a particular beta I contribute, and how does it do it? And then the partial F test will give us the question, maybe some of the predictors explain the variability, by how much. And that'll be the partial F test. In some sense, that's the main part of this section. Now all of these we can use for tests of hypotheses or confidence intervals. So the question of the day again is, do any of the predictors add value? So our null hypothesis is going to be, no, none of them do. Beta 1 is equal to beta 2 is equal to beta k is equal to 0. All the coefficients are 0. They add no value. An alternative hypothesis, there is at least one beta I that's not 0. This kind of reminds us of the story in Genesis 18 where Abraham is outside of Lot's city of Sodom and Gomorrah, and he says, Lord, will you destroy if I can find 50 righteous? And he keeps on going down to 10. Well, we're going to keep on going to one contributor is found there, then we're not going to destroy the whole model. Remember, if you're saying all are 0, if you take the negation of that, you're not saying all of them are not 0, you're just saying that at least one of them is 0. It's sort of like saying all Wanget's men wear sweaters. Well, the negation of that is not all Wanget's men don't wear sweaters. Some of them may. It's just at least one does. So we'll have sort of a call and response here. So the people say we need a statistic to measure variability. Since we can't use R-squared, we need to have some sort of numerical value that will help us. And so I will say, as leader, we do have numerical measurements for variability. The sum of squares total, sum of squares regression, and sum of squares error. And since statistics is about measuring variability, we ought to have something like this. Well, we do know that the mean square error is roughly equal to the model's variance, or in other words, in terms of standard deviation, the square root of the mean squared error is equal to the standard deviation. So maybe we can use that. In all cases, no matter what kind of assumptions we make, the mean square error equals the model's variance, or in other words, we take the square root, we get the model square root. The people may say, well, what if the null hypothesis are true? After all, that is what we will be assuming. We'll be assuming that all the predictors are 0. Well, if we assume the null hypothesis is true, then the predictors are useless. We can just throw them away. If that's the case, then the sum of squares regression would be a good measurement of the variability of the data. Again, assuming the null hypothesis is true, that none of the predictors have any value. But regardless, sum of squares regression is independent of sum of squares error. So the MSR would also equal the model's unknown variance. In other words, If the null hypothesis is true that the prediction had no value whatsoever, none of them, then S would be equal to the square root of MSR. So then they might respond, if the null hypothesis is true, then they're approximately equal. In other words, if we take the ratio, they should be approximately equal 1. Ah, yes. But remember, the data could have been different. We're not getting perfect knowledge. We're only getting this from the data. So we could get some sort of variability. And people, you all get an F. I mean, the F statistic. And the F statistic is the ratio of the mean squared regression over the mean square error. So therefore, the greater F is from 1, the greater the evidence against the null hypothesis that no predictor has utility. So that's the statistic we're going to use. And nicely, we can find the statistic for the overall test in the analysis of variance table. If you take a look at the analysis of variance table, you get that the F is right here. This is the value you want to use. And it's the ratio of the mean squared regression over the mean square error, 19.48 over 1.78, and you get the 16.64. So that's very nice to have. So, okay, so we have this F statistic. If the null hypothesis is true, what distribution does our test have? Could we simulate this? Sadly, we can't simulate it because it's a little too complicated for our understanding at this point. But if the null hypothesis is true, the test statistics will have an F distribution. The numerator will have k degree of freedom. Remember, k is the number of predictors. And the denominator will have the same degrees of freedom as the error. That's n minus k minus 1. And still, unfortunately, it's difficult to simulate with multiple predictors. But still, we're getting someplace. And so you may ask, how should we shade the F distribution to calculate the p-value? Well, we always go right. Recall, we're looking for evidence in favor or more favorable to the alternative hypothesis by definition of the p-value. So we'll always shade right of our F distribution. Notice the little slide figure that the F distribution has. Well, how can I use Minitab to calculate the p-value of an F distribution? Well, we can do that. So let's do some examples of movie revenues. Does production costs, promotion costs, or book sales help predict first-year box office receipts? And I just took some small data. There you can see in the lower left-hand corner what the first-year box office receipts are. So I'm saying, do any of these help predict? I'm going to say no. None of these variables help predict first-year box office receipts. So beta 1 equals beta 2 is equal to beta 3 is equal to 0. My alternative is that at least one of these beta i's is non-zero. At least one of these predictors have utility in predicting first-year box office receipts. There's no use of going through all the process if none of our betas have any utility. So the overall F test is like one of the first things you do after you do your residual analysis and stuff. So again, you can see down here that the mean squared regression is 3310.82 and the mean square error is 56.87. We put those together and we get an F statistic of 58.22, which is, hey, right there as well. So you can see how we have it here. If you're going to use Minitab, you need to do the probability distribution plot. Make sure you select the F distribution with 3 degrees, whatever the numerator degrees of freedom and the denominator degrees of freedom will be. And then make sure after you select the distribution, make sure you take the shaded area, and then you're either going to do the probability or X value. Remember, always going to go right. Here I enter in the 58.22, and I get a p-value that's really, really small, 0.007933. So at least one of these predictors is right. I mean, has utility for our model. So what we would say is, with the p-value of 79 times 10 to the 5th power or something like that, we have very strong evidence to reject the null hypothesis and say at least one predictor variable gives utility to the model. Now let's try one where I tried something else. So here I just made up some names, people I knew, Bob, Amy, Cabrera, and I just made up them some test scores, and I wrote down their height, and then I kind of estimated how many hours from home they were, and then I just wrote down some digits from pi, not in order because I don't know the first 6 digits of pi, let alone 100 or 1,000 like other people do. So let's go ahead and do stat, regression, and fit the regression model with test scores and these 3 predictors. And what happens here is that you get a mean squared regression of 586.88 and a mean square error of 290.90, which is pretty close because their F value is 2.02 and the P value is 0.2. So we would fail to reject the null hypothesis and kind of say we have evidence that none of these predictors have any utility in predicting someone's test score. Now, it's just some advice. The overall F-test will be different than some of our other F-tests that we'll be using, like when we're just looking at one predictor or a subset of predictors. In other tests, sometimes we don't want to reject the null hypothesis, but in the overall F-test, we do. So we want a large F statistic. When we start talking about the partial F test, it'll likely go the other way. We're going to want to reach a point where we cannot reject the null hypothesis. In that case, we'll want a smaller F statistic. So just don't get in the pattern of looking for a large F statistic and saying, hey, that's great. Sometimes later on we'll want a smaller F statistic and saying that's great for our particular situation. All right, so you might want to look up Psalms 53 and Genesis 28. 28, was it 28? Yeah, or sorry, 18. Look up Genesis 18 and realize that our worth in God does not come from our usefulness or our utility, but that He is imputed righteousness through Christ's love. Okay, I'll see you in lesson 2, or I'm sorry, video 2 for lesson 4. See ya.